Right. Good afternoon and welcome. It's my pleasure to introduce our colloquium speaker today, Dr. Wenwu, Professor in Mechanical Engineering. Professor Xu is an expert in multi-scale modeling of materials, both at atomistic and molecular level. He's also done extensive work in microscopy and electron microscopy and X-ray microscopy and merge experiments with some interesting modeling work. His training as PhD was from the University of Beijing, and then he's done postdoctoral research at
University of Manchester,
and came to UC Merced, and we were very lucky to snag him and get him to come to SDSU. And today he's going to share with us some of the work he's doing on understanding metals. Go ahead.
Fantastic. Thank you very much for the very nice introduction. I was surprised you could remember my experiences before. Thank you. I really appreciate that. So I am mostly 70% of my research effort is focusing on computer simulations at multi-scale, from microscale to nanoscale to atomistic level. And then 30% of my effort is experimental characterization of the microstructure that we could simulate from the all sorts of different computer simulations. And then we combine these two together to be able to get a better understanding of what exactly is happening of the material, particularly mostly for metals and ceramics, under all different kinds of responses. And today's talk will be mostly focusing on a few of our recent work using atomistic level computer simulations, specifically molecular dynamics simulations, to study the mechanical properties of metals, specifically nanoscale metals. Now, the title of my talk is talking about the deformation mechanisms of light-weighted nanocrystalline metals as a very important type of nanomaterials. And the talk is going to be outlined. I would like to give a little background why we wanted to study the light-weighted nanometals. And then I would spend a little bit of time to talk about the method we were using to study the deformation mechanics of those metals. And then I will just present two studied results of nanocrystalline magnesium and aluminum, because those are the very typical type of light-weighted metals for real applications. And then we want to leverage our idea or understanding from those study results, and then to be able to design some new microstructure to tackle some new challenges of the realistic applications for metal applications, for example, the fatigue properties of metals. And we know the majority of the failure in engineering parts, they are mostly coming from the fatigue. And then we will see, okay, can we engineer the microstructure from the theoretical point of view to be able to improve the fatigue property of metals? And then quickly just conclude what we will talk about later. Light-weighted metals, this would give us a huge benefit in terms of the reduction of carbon footprint and saving the energy, especially imagining if our transportation applications using much more lighter metals, of course, with sufficiently strong mechanical properties, and then we could save a lot of energy in terms of the transportation, and this would actually contribute approximately 15 to 20% of the carbon footprint all over the world in the transportation field. So if we can reduce the energy consumption due to the lightweight design, and then it would give us a huge benefit. And of course, it would not only in the transportation, in the aerospace and the space satellite, the employment of those lightweight metals would always give us additional benefits. And specifically we are mostly interested in aluminum and magnesium simply because they are relatively cheaper, and then they have the potential to be able to have a higher strength through all sorts of different engineering. And of course, our idea is to use nanostructuring, specifically nanosize effect, and also understand the nanomechanics, which is the deformation of nanomaterials that is a little bit different from what we could see in the traditional materials. And then once we have some good understanding of this, and then hopefully we will be able to come up with some practical ways to improve the mechanical properties of those aluminum and magnesium-based alloy. Now, when we talk about the nanomaterials, it means a lot of things. It pretty much means everything. And in this talk, we are going to focus on the nanocrystalline microstructure. And this is in the form of a bulk metal, except the grain size is under 100 nanometer. So this would be, if we do not see the scale of this model, it could just like a microcrystalline or conventional metal microstructure. But in a 3D nanocrystalline model, the grain size is less than 100, average grain size is less than 100 nanometer, and then we have plenty of grain boundaries. And these grain boundaries is so high density in the 3 volume, it would actually contribute to the mechanical properties and the microstructure in a significant way. Yes, please.
Just for comparison, what is the typical grain size of manufactured metal?
In this case, it will be under 100 nanometer, from a few nanometer to...
I meant to compare nanocrystalline materials to conventional materials.
Microcrystalline material.
Yeah, but how much larger are the
Regular ones.
Regular ones is from a few micrometer to a few hundred micrometers. This would be a regular grain size for the metals we are using. For example, these are the cast aluminum. Of course, it's alloy. I would assume the grain size is probably a few micrometers on average. That's a very nice question. Thank you. Right, and there are report. Oh, sorry, I don't like this table. Sorry. No, it's okay. I'm just kidding. I'm sorry. I'm just kidding. There are different deformation mechanisms, and for these microcrystalline metals, in which the grain size is a few tens of micrometers, and then the deformation mechanism is dominated by the dislocation in the plastic range. In a conventional metal microstructure, the dislocation would easily generate it inside the crystal, inside the grain. We call this a grain, and then surrounded by the grain boundary in the microstructure. And then those dislocations can easily generate it in the grain, and then it is going to accumulate it. It's going to move and accumulate along the grain boundary. And in this, the dislocation and as well as the deformation is taking place. Yeah. But this is... define dislocation for your audience. Okay, very good. The dislocation is a kind of one-dimensional defect in materials, especially critical for metals. When we are deforming a piece of metal, then initially we have elastic deformation, and then nothing is supposed to happen. And nothing significant is supposed to happen. But once the metal is becoming into a plastic range, which means permanent deformation of a piece of metal, then a very important type of defect, which is a so-called dislocation, is going to come in. And once the dislocation is generated, and then it will keep generating with increasing the plastic deformation. And then the more plastic deformation we have in the metal, and then the more dislocation defect is going to be generated. And then this dislocation is actually going to move across the crystal or the grain of the material during the deformation. And then this motion of all sorts of different kinds of dislocation will start to accumulate at the grain boundary. And then eventually, when this kind of accumulation is significant enough, and then it's going to accumulate lots of stress at that region, and later it is going to become the nucleation of crack inside that region, and eventually it's going to cause the failure of the metal with sufficient amount of plastic deformation. Right? And the other thing I want to mention is this kind of dislocation is basically atomic level defect in the material. It's a line of defect inside the material during the deformation, plastic range. And this is the major deformation mechanism for very large grain size metal during the plastic deformation. But for the nanocrystalline material, in which the grains are relatively less volume fraction, and then we have lots of grain boundaries inside the nanocrystalline material, and that would actually provide additional contribution to the deformation mechanism, and especially when the grain size is very small, like a few nanometers or maybe a couple tens of nanometers, then we have very, very high grain boundary density, and that would actually becoming, for example, the dislocation sinking area during the deformation. So what does that mean? Instead of accumulation of those dislocations, the dislocation generated is actually sinking along the grain boundary area, simply because there are a lot of grain boundaries, and also the grain boundary has much more excess volume compared to what you could have inside the micro-sized or the crystalline microstructure. Now, this is another additional one is because those grain size, they are so small, during the deformation, they can actually start to slide relative to each other along the grain boundary inside the nanocrystalline material. And this is rarely could happen inside the microcrystalline material, simply because it's going to require much higher energy. And also we would be able to see some grains, small grains rotation as well inside very small grain size level. And these are some reported mechanisms in the literature. Now, for each different type of materials, this is not necessarily very helpful for us, because we want to know more about the quantitative information so that we can actually use this as a design base. And that's what we are going to do using the molecular dynamics simulation to be able to quantify those deformation mechanisms as a function of the grain size, so that we will be able to have a better design. Now, the molecular dynamics simulations is a very good tool to be able to study this kind of mechanical deformation behavior, because those defect activities, dislocations, grain boundaries, they are atomistic level defects. And then, of course, the molecular dynamics simulations will be a very good tool to be able to see the evolution of those defects during the deformation. Now, the general steps of running a molecular dynamics simulations, we need a model first. Just like when you're doing experiments, you need a sample first, right? And then the next is, I would like to conduct a simulation. In this case, it would be a mechanical deformation simulation. Just like when you are conducting the experiment, you use some kind of equipment to conduct a mechanical testing, like a tensile testing or compressive testing or some other, or indentation testing, etc. And we do exactly the same thing in a simulation. And then the results from the simulation would be also very similar that we could get from the experiments. In the experiments, from the tensile testing, we can get some stress and strain curve or some other mechanical properties from the testing, and we could get exactly the same type of information from the simulation. In addition to this kind of information that you can get from the experiments, we could get exactly the atomistic level evolution of the nanostructure change, and we can trace the dislocation generation and see how the dynamics of those dislocations is taking place during the deformation. And then we could quantify the dislocation. And of course, this kind of things in theory can be done in experiments. It's just very, very difficult to capture those information, you would need extremely expensive equipment to do that. As far as I know, there are probably only a few labs in the entire world is capable of doing such kind of characterization at the atomic level to be able to see this in dislocation dynamics at the atomic level. However, everybody in this class will be able to do that simulation I'm going to talk about. Right, so this is a great advantage. Now, in terms of the model construction, we would like to create a series of models with different grain sizes from a few nanometers, a couple of nanometers to, in our case, it's approximately 50 nanometer on average of the grain size. And then we create the series models from small to large. These just give you a few examples how that model is look like, the nanocrystalline magnesium model look like. And then the volume of this small model is approximately 100 cubic nanometer. This sounds really small, but there was a really fancy technique in the molecular dynamics. It's called periodic boundary conditions. And then that means the one side of this model is exactly equivalent to the other side of the model in the opposite direction. And that means we are basically simulating a infinitely large model, but of course represented by this small volume. And this would give us a relatively more realistic simulation results that we could compare with the experiments. And then the system is consisting of approximately 100 million atoms in each one of those models. So that means this is not a few, not a small amount of atoms in the system. So that means we need the supercomputer to be able to conduct this kind of simulation. And the good news in our university, we have a pretty nice, a reasonable size of supercomputer cluster on campus, which is called Fermi. In there, we conduct most of our molecular dynamics simulations for our research. And you guys, if you're interested in, feel free to get in contact. And then if you want to make use of those facilities, you are very welcome to use it for your research. And then the next thing is we're going to conduct simulation. And for simplicity, we would conduct a uniaxial tensile testing. So what does that mean? So imagining I have an initial model, I'm going to just elongate or deform this model or this model along certain direction, gradually, just like when we are doing this kind of uniaxial tensile testing. And then we will observe what exactly is happening in this model and how can we quantify the dislocation density and what is the mechanical properties of this model. Exactly like what we are doing in experiments. Okay, so now I would like to present two representative simulation results of nanocrystalline magnesium under uniaxial deformation. So before I play the video, I'd like to give you a little bit heads up of some basic information. Otherwise, it's going to be, you will feel a little bit overwhelming. There are a lot of things happening. So first of all, let's take up this model. So the blue color is representing those. So you don't really see the single atom here. In fact, in this, this is a side view of the model. In this model, it's actually containing approximately 45 million atoms. So that's why you are not able to be able to see a single atom because it's just too many here condensed. And then the green color, they are the green boundaries. And later you will see something that looks like red color, and that will be the stacking faults, another type of defect that is usually existed in metals. And then the green color later that you are going to see that it's kind of moving across the sample, that is going to be the dislocations we are looking for. And now let me play the video and then please focus on those moving green features in those different regions and see what is happening to them. And then initially there was nothing because it's still in the elastic range. And then once it crosses the plastic range, and then we can see a lot of things is happening. like this grain feature that is moving across the grains, and then including this region, and then we would also see this grain feature is also moving, and then moving across the crystals, and then it's actually accumulating more and more when the plastic deformation is slowly happening along this direction. And you can clearly see the accumulation of those grain feature, which is dislocation inside the grain during the plastic, with the increase in the plastic deformation. This is exactly what we know from the traditional materials, that the dislocations is going to be generated, and then they are going to start to accumulating more and more against the grain boundary, which later you can imagine when these dislocations, they start to accumulate a lot, then the stress level in that range will be becoming higher and higher, and at some point it is going to form the manipulation of the crack or causing the failure of the materials. Yes, please.
What's the maximum strain in that simulation?
The strength is 50%.
50%.
Yes. Right. This is pure metal magnesium. So compared to alloys, this is significantly high.
When we start with the initial crystal structure that we generated from the raw line,
Yes.
can you say something about how you model those? What do you do for the grain boundaries? Because this is an atomistic scale,
Yes.
right? So do you evolve the atomistic representation of the grain boundary, or is it purely random?
Very nice question. So the grain boundaries in the model we created, they are random. Simply because the orientation of each grains, they are as random as possible when we created the model. So we would expect those grain boundaries. There may be some special grain boundaries, but I would assume that's a very good question. I haven't done that kind of statistics, but I think those grain boundaries we created, they are mostly random. Especially when we have a lot, like a few thousands of grains in one model. I think that would be the case. Yes, please.
I trying to understand you said that you use periodic boundary conditions
Yes.
and you show some blocks.
Yes.
So every piece in your model is a cube?
Yes.
Cube?
Mm-hmm.
Okay, and what made you, what is the periodicity? Because a periodic boundary condition is for a phenomenon that you know that is some periodicity that
Yes.
you are,
Yes.
which is basically mean you don't have boundaries.
Right. Exactly. Very good question. So imagining I may have a dislocation generated, and then it's going to move into here, and then it is going to showing up from the other side of the model, as if this side is exactly the same as this side to achieve the periodic boundary condition.
No, I know how it's done.
Uh-huh.
Just saying, in this context, what is the reason? Because not everything you can put periodic boundary condition.
Yeah.
What makes you? What is the reason that here it works?
Oh, thank you very much. This is to avoid the surface effect, right? So imagining if we do not apply the periodic boundary condition, it's going to become a particle with a lot of surfaces, and that would be a great way to simulate the nanoparticles if we do not apply the periodic boundary conditions. And here, the only reason we apply the periodic boundary conditions is to mimic the bulk property. Yes, please.
But there isn't correspondence structurally in terms of the green boundaries between the sides. So I don't understand how this would work, I guess.
So yeah, this is the side view. In fact, the model is kind of 3D, so that's why it looks a little bit confusing.
Right, but I'm just saying, you know, you have these large green boundaries on the lower left, the left side.
Like
There
this
aren't
one?
any on the left side of the cube. But there isn't something comparable on the right side. I mean, it just looks like structurally, if you have it isn't periodic in structure. So how do the periodic boundary conditions work? You get what I'm driving at? I mean, that dislocation boundary on the left,
Mhm.
And it isn't the comparable thing on the right where you're applying a periodic boundary.
Yeah, this is because this is side view, and if we are able to rotate it 90 degrees, and then we will have a better view of the side
Oh, okay. I see.
microstructure.
But it still seems like there should be something green on the right side.
Yeah,
Green on the
imagine
left side.
imagine this green is actually a 3D.
Yeah, yeah, I
particle,
understand.
right?
So your chloride cells, just repeat the geometry is 50 values.
The
So when you generate your chloride
Mhm.
oscillation,
yes.
at the boundary state, they need the periodic zero, right? So we exactly have the same locations of your great boundary.
Yes, in between the center of the Bernoulli cells, there will be a green boundary located. And then depending on the distribution of those Bernoulli center, then the green boundary will be located in a different, the center of those any two Bernoulli center points. Okay, thank you. And then this is for the 45 nanometer average grain size model. And then the next video I would like to play is for a much more smaller grain size model, and it is approximately 6 nanometer. And then once I play the video, then I would like us to focus on the similar feature and then see what is the difference between these two grain size case. And then we have this, initially we have elastic deformation, and then once we reach the plastic branch, and then we started to see some plastic deformation behavior. We can see in some rare cases, we have a little bit dislocation formed, but the more amount of the grains doesn't really show this kind of dislocation accumulation. And then where are those dislocations coming from? And where are those stress compensation coming from? There has to be a way to compensate the stress we applied during the deformation. And that is a good suggestion that something additional is happening in addition to the dislocation contributing to the stress compensation during the deformation. And that is the grain boundary effect, as we expect, as we learned from the knowledge in the literature. And then this is exactly what's happening. And we would like to look into more in detail and analyze all of those structural changes in a quantitative way so that we have a better understanding of the deformation mechanisms. One is the dislocation dominated deformation mechanism, and then the other one is grain boundary dominated deformation mechanism. Now, if we take a little bit closer look, in addition to the dislocations that is generated, and what is interesting is we actually also observed some nano twinning, which is interesting because in the experiment, it is also observed the formation of those nano twinning. And what is more interesting is in the even very small grain size of nanocrystalline materials, the nano twinning is not that often seen. It's actually, in fact, it's very rare to see in a small grain size, but in a relatively larger grain size model, like 45, 50 nanometer, or 40 nanometer, we see lots of nano twinning formation. And it's during the deformation. And then the other thing I haven't mentioned is those red features, those stacking ports. In fact, they are the, imagine I have a dislocation form. In this particular case, I'm mentioning the short-lived partial dislocation, which is a special type of dislocation that is mobile during the deformation. And the trace that is leaving behind this kind of dislocation would result in the formation of those stacking ports, which is another type of effect formed during the deformation of the metal, right? Okay, now this is an overview of the deformation in a larger grain size, but in a smaller grain size, I would like to also study this grain boundary effect. What exactly are these? So first of all, okay, let me just focus on just 2 grains to be more specific, G1 and G2. And then let's see what's happening between those 2 grains during the entire deformation process. And then one thing we have noticed is, and you can see this relative size of G1 and G2. So initially they are kind of more or less close, and then when the plastic deformation start to have more and more, and then see there was a relative size change. This does not necessarily mean one particle is kind of engulf another one. This is just simply a sliding of the grains along the grain boundary that is in the direction that is perpendicular to the grain. Because this is a 2D view of a 3D. It's kind of sliding in the direction that is perpendicular to the grain. And then we also noticed some kind of relative orientation change of those 2 grains during the deformation. And this, and specifically in this case, is approximately about 2.64 degrees. And this is also reasonable compared to what experimental study reported, a couple of degrees during the deformation. All right, now that was just some kind of overview. I would like to quantify the dislocations so that we can have a better understanding of the deformation mechanism. So what I do is I calculate the dislocation density for each one of those models and plot it out as a function of the deformation process. For example, this light blue color, this is representing the dislocation density for the grain size of 6 nanometer throughout the entire processing. I do the same thing for all the other grain sizes. Even though the dislocation density, they are not strictly following the monotonic behavior with increasing grain size, we have an increasing dislocation density. This is not exactly that case, but approximately with increasing the grain size, the dislocation density is increasing. That means at larger grain size, the dislocation is more important, behavior is more important. And then in a smaller grain size, the dislocation is less important. That means in a smaller grain size, the grain boundary deformation mechanism is supposed to be more significant. And that's exactly what we observed. And that you can see the in a smaller grain size, the change in the density is relatively small, but for a large grain size, the dislocation density change is relatively larger compared to the small grain size. And we want to further quantify this kind of effect. So what do? There is a very nice classical way before the invention of the molecular dynamics simulations. People use the analytical way to be able to quantify the dislocation behavior. And that is a so-called Rovans equation. And in this equation, this is a very simple analytical equation. And the rho here is the dislocation density, which is what we computed here. And then this gamma D, this B here is the Burgers vector, which is a physical property describing the feature of dislocation defect. And this D here is the grain size of the material. And then we want to use this equation to, because this is a grain size dependent parameter, and then we use an analytical function, and then we plot it out, the dislocation as a function of grain size, then we will be able to see this curve. And this curve is described by this analytical equation. And then what we really calculated from the molecular dynamics simulation is this dotted dash curve here. And you can see when the grain size is smaller than about 20 nanometer, there is a significant divergence between these 2 mechanisms. And in the analytical equation, this is purely assume that deformation is caused by dislocation dominated effect. But in our molecular dynamics simulations, this is actually not that case. So that means when the grain size is less than approximately about 20 nanometer, the dislocation dominated deformation mechanism is no longer the most important mechanism here. The grain boundary dominated deformation mechanism becoming more important. So this is what tells us the rough transition between dislocation dominated deformation mechanism to grain boundary dominated deformation mechanism is approximately about 20 to 25 nanometer. So this would give us some kind of idea once we would like to design a piece of metal according to the nanosize effect. Right.
So is the strain important for plastic strain or total strain?
Which one? Oh, this is the total strain.
So if it is elastic, why do you get dislocation density change?
This is because in the initially created structure, there are some partial dislocations situated at the grain boundary region. Very good. Thank you very much. That's a good question. Okay, so this tells the same story I just talked about. So I'm going to just skip that. I just want to reiterate though is a gradual transition from the grain boundary dominated deformation mechanism to the dislocation dominated deformation mechanism with increasing the grain size, right? Even though the rough transition is approximately about 20 to 25 nanometer, but in fact, this transition is not abrupt. It is a gradual transition. Okay. Now, we also would like to examine our results in terms of mechanical properties with literature results, and then we computed the flow stress during the plastic deformation. This is our simulation results at different grain size level, and then this is the reported literature results. It seems like we have reasonably well correlation that compare with the experiments. However, you may notice there was a difference. There was a difference in absolute flow value. This is because in our model we deform even faster. That's why we have a higher flow stress inside the material. But the overall shape of the flow stress looks close enough, reasonably a good agreement. Now we also compare some mechanical property like elastic modulus of our model to the data available in the literature. For example, we computed some single crystal magnesium just for comparison, and then we can see the nanocrystalline, the elastic modulus of the nanocrystalline model is somewhere in between the single crystal model, elastic model, which kind of makes sense. However, what is interesting is when the grain size is small enough, the elastic modulus is significantly decreasing, which suggesting there was a softening effect of the metal when the grain size is small enough, which is also what people observed in the experiments. When the grain size is extremely small, there is indeed a reduction of elastic modulus of the metal. Right, so quickly summarize for the magnesium, in a nanocrystalline microstructure, we semi-quantitative described those two distinct deformation mechanisms, dislocation dominated deformation mechanism, grain boundary dominated deformation mechanism. And then that transition is approximately about 20 nanometer. And that transition is a gradual change, right? So this is these results about nanocrystalline magnesium. And then I would like to quickly mention, we also did some similar results for the aluminum, as aluminum is also something we are interested in as a major metal source for lightweighted metal alloy design. And then we all do the same thing, set up the model, and then we perform the mechanical testing, which in this case, again, the tensile testing, and then we quantify the dislocation, and then study some nano deformation mechanisms. We do exactly the same thing like what we did in the magnesium. And then this is probably a little bit boring because we observed something similar, just a little bit different, which I would like to emphasize in a minute. So for example, I create, of course, a series of models from small grain size to larger grain size. Here, I just want to show one representative model for a grain size of approximately about 4.4 nanometer. And then we just conducted the tensile testing, and then we observed a lot of dynamic features that is evolving throughout the deformation. And then we also conduct the dislocation quantification for each one of those samples as a function of the deformation process. And then for the smaller grain size to larger grain size. And then we see there is a similar phenomenon like what we just talked about in the magnesium, that is with increasing the grain size, the dislocation density is increasing relatively. And then this can be nicely described by this analytical curve. That is indeed, with increasing grain size, the dislocation density in a plastic range, flow stress range is also increasing, not linearly, kind of like non-linearly, right? And then, so this is just an overview. I want to take a little bit of time to look into what exactly is happening in the elastic range, because initially we thought nothing is happening in the elastic range. In fact, there are some kind of activities that is happening during the elastic range of this deformation. There are, in fact, some kind of point, what you are seeing here, those are actually the point defects, those dots, those light dots inside the grain, those are the point defects. In fact, during the elastic deformation, there are some point defects that is caused by the lattice distortion that is kind of happening, disappear. So this is the most significant events that happen in the elastic range. And in a plastic range, of course, we see lots of dislocations, and then also some other deformation mechanisms like grain boundary migration. For example, we see this grain boundary here, and then there is a grain boundary migration, and this is actually associated with the dislocation activity as well. It's as if there are lots of defects here, and then it started to nucleate the dislocation and then kind of inject the dislocation to somewhere else. And then at the same time, the grain boundary will start to move dynamically as a result. And then in addition to that, we also observed some nano twinning in the nanocrystalline material. This is a little bit different from what we see in the magnesium, because in magnesium, we only see the nano twinning formation at very large grain size. But in aluminum, we actually see the nano twinning even at a very small grain size that is approximately 4 nanometer. And so this is the difference. I think we don't know the reason exactly, but it probably associated with the different crystal structures. In magnesium, it's HCP crystal structure, but in aluminum, it's FCC structure. Maybe this is associated with that, but we don't know exactly the reason yet. And then we would also like to compute the mechanical properties and then compare with the literature data to see, just to verify our estimation results. And then we also computed some the strengths, the yield strengths of each one of those models from larger grain size to smaller grain size. And then we see a relatively good correlation between the stress value, the yield stress value coming from the literature or from the experiments with our simulation results. And again, the difference between the absolute value that is coming from in the literature or in experiments, the deformation is way more slower than what we conducted in the molecular dynamics simulations, which, by the way, this is a major disadvantage of molecular dynamics simulations. That is, we could only simulate a material deformation at very fast strain rate due to the limitation of the simulation method. Right, and then we also compute the elastic modulus of the nanocrystalline aluminum, and we also see this softening effect or reduction of elastic modulus when the grain size is very small, similar like what we see in the nanocrystalline magnesium. Okay, so we've done the mechanical study and understand the nanomechanics, the deformation mechanisms for nanocrystalline magnesium, and aluminum. So what can we make use of this? Can we make use of those understanding we learned, those knowledge we learned from those kind of simulations we have conducted so far to do something else? And one thing we are thinking about is, can we design some unique, theoretically unique microstructure so that we will be able to improve mechanical properties of the material? For example, we are very interested in the fatigue property of metals because the fatigue failure is estimated to be involved in 90% of metallic failure in mechanical parts. And then if we look back and find out the basic reason why fatigue is causing the metal failure, and this is due to the accumulation of dislocations against the grain boundary. And you can imagine lots of dislocations generated, and then they move towards the grain boundary and accumulate over there, and eventually those regions will becoming the very high stress region. Later, it will becoming the stress concentration and the nucleation of failure sites. And the other thing is, this kind of process is usually irreversible. That's why fatigue failure is unavoidable in most of the cases. So what we are thinking about is, can we design some kind of unique microstructure to be able to avoid this kind of phenomena? For example, can we have the dislocation reversible through a microstructure design? So that is what we tried in the in our research. Using molecular dynamics simulation methods based on the knowledge we just learned from the nanocrystal material. And if you may recall, for nanocrystal materials, when the grain size is very small, the dislocation generated, and then they're going to sink, disappear in the grain boundary region, right? So that means the grain boundary, those nano grain boundaries would actually act as some kind of sinking of dislocations. And that means we are actually potentially be able to avoid the dislocation accumulation by introducing lots of those nanograin boundaries. And that is what we are trying to set up theoretically in a new microstructure. That is, for example, okay, so if I started with a microcrystalline structure in which we have the grain size from a few micrometers to a few tens of micrometers. And then if we are able to manipulate the grain boundary and then replace those grain boundary by the nanocrystalline structure. So that means we have a network of nanocrystalline grain boundary. And then imagining if there was some dislocation generated inside this crystal, and then it's going to move to this region, this network. And then because those network regions exist lots of nanograin boundaries, they're supposed to be able to absorb those grain dislocations. And then we can avoid the accumulation of the dislocations. Okay, so this is the initial idea that's examined from the atomistic level to see if this is the case. Right, and then of course, we cannot simulate the entire model, it's just going to be too big. So we only will be able to simulate a tiny small section. And imagining this would be the net part of the network of the nanocrystalline structure. And then this would be the grain interior coming from that large grain. And then we would like to apply some fatigue testing to see, and then track the dislocation, what is happening in there. Right, and then we can apply this sinusoidal fatigue testing, which is a very typical type of mechanical fatigue testing in experiments. And then, of course, we want to compare with some other scenarios so that we can have a better understanding. For example, we can conduct exactly the same fatigue testing for a single crystal model, or we can conduct that for a microcrystalline model in which we only have one grain and boundary in the center. And of course, there was another one due to periodic boundary conditions. So there are two grain boundaries in this model so that we can represent it as a microcrystalline structure. And then we can also do exactly the same thing, the fatigue testing for the pure nanocrystalline model. And then this will be our targeting design where we have this kind of nanocrystalline network on separating these micrograin matrix. And then we conducted the fatigue testing for all of them. And then from the overview, it looks, nothing is, we don't know what it's looking at, because though, yes, we see a lot of dislocations, but it's kind of a hidden structure inside the model, so we can't really see a lot. However, it works. The microstructure is kind of maintained throughout this fatigue testing, which is good news. The next thing is, let us just remove those atoms, only show you the dislocation defects. And then let's show the video, and you can see in a single crystal, immediately the velocity dislocation generated. And then in the microcrystalline, it's also kind of similar. And then in the nanocrystalline, you can see those dislocations. They are coming from the grain boundaries maintained. There was no significant amount of dislocation increased. And then what is interesting in this case, in a bimodal case, is this is also a single crystal particle. If we compare to the single crystal, we can see within the same deformation mechanism, we see a lot of accumulation of dislocation remained. But in this case, we don't see that much. So that means the presence of that nanocrystalline, by the way, I kind of make it invisible of the top part. It's supposed to be look like that on the top part. But what is happening is at the bottom part where the single crystal is located, we don't really see that many accumulation of dislocations as you could see in a single crystal. So that means the presence of this nanocrystalline part indeed helped us to achieve less accumulation of dislocation in a crystal, in a single crystal, right? So this is probably still not that straightforward. Let us plot the dislocation density as a function of the fatigue cycle. And then we can clearly see the dislocation in single crystal, and in the microcrystalline structure, it increases rapidly and maintains a certain level after a few cycles of fatigue deformation. And in a nanocrystalline, it's kind of expected. We don't really see a significant increased amount of dislocation density because the dislocations, they are kind of formed, but they sink and disappear at the grain boundaries. And in our case, oh, by the way, I call this as a bimodal model simply because we have a nanocrystalline and a microcrystalline component. And then in the nanocrystalline component of this bimodal, it behaves similarly like a pure nanocrystalline. But what is more interesting is in a micrograin matrix, we do not really see the much accumulation of the dislocations, exactly like what we just saw in the dislocation animation, right? So this tells us, then we look into why the presence of this nanocrystalline network would reduce the accumulation of the dislocations in the micrograin grains. And then we examine the grain boundary width in the nanocrystalline component of this bimodal microstructure. And we actually noticed a little bit the width change of the grain boundary in the nanocrystalline component during the fatigue cycle. And then it's not that much, it's approximately 1 or 2 atomic width change throughout this entire fatigue cycle. And in fact, this gives us an idea that this is because you can imagine when we are doing the compressing, the grain boundary has some additional spaces that it could buffer the external forces applied on the material during the fatigue cycle. And then once we have a dislocation that is generated, and then it is getting pushed into the center of this grain. And then once we release the external forces, and then the dislocation is actually moving back towards the grain boundary and going back and sink in there. So this is what we think that is happening. But let us take a look at one example. One example that we take a closer look to examine this kind of dislocation generated the grain boundary and moving to the crystal and then going back. So this is kind of reversible behavior of the dislocations during the fatigue cycle. And then let's see, we have a grain bound a dislocation generated, and then it's going to propagate through the center and moving back to the dislocation grain boundary. And then let's see another example. And then we also see a dislocation generated, and then during the release of the force, and then the dislocation is moving back, and then there's another example. And then you can see, indeed, we see some kind of reversible dislocation motion. And imagine it, if this can be implemented in a realistic material, and then it is possible to be able to largely enhance the fatigue property of the material, because we have much less accumulation of dislocations. Thank you very much. Yes, please.
How would you manufacture that material?
Great question. This we recently got the fund from the DOE, and the idea to be able to manufacture this kind of microstructure is we are going to take advantage of the electrical resistance between the grain boundary and the grain interior, because the grain boundary, the atomic disordering is much greater than inside the grain. And then if we are able to pass appropriate condition of electrical current, and then we are supposed to heat more of those grain boundaries compared to the heat inside the grain, simply because of the larger resistance at the grain boundary. And then when the power is sufficiently strong, and then we are supposed to be able to melt the grain boundary without melting the entire material, and then quickly crystallize it at those grain boundary regions, we will be able to form, hopefully, this nanocrystalline network structure.
Is that analogous to annealing?
Say again?
Is that analogous to annealing?
Except we will have to use a very high electrical current within a very short amount of time. Because imagine if the heating is too long, the heat that is generated, the different heat that is generated at the grain boundary, and the grain would be already homogenized. So the powers will have to be short enough to maintain this heat difference between the grain boundary and the grain interior. Very good point. Thank you. Yes, please.
You kind of mentioned earlier about the weight being a factor of this, like we want lighter materials as well. So how does weight factor in with this new structuring of the material?
Like
the weight of the material, like how much it weighs.
For magnesium and aluminum both?
Well, we're doing this new method of composing them with the nano.
Oh, you mean the bimodal structure?
Yeah.
This would be pure. In our case, of course, we modeled it as pure metal. But imagine if I have an alloy, and then we do not really need to add or remove any element, then we just need to engineer the grain boundary so that we will be able to have this kind of special microstructure. So there is no weight increase or loss. Because usually in the traditional way, if we would like to improve the mechanical properties of aluminum or magnesium, we usually have to add a lot of heavy metals. Sometimes has to be a large fraction. So that means even though we are increasing the strength of those lightweight metal, but in the meantime, we are practically increasing the weight. And in this case, it's purely microstructure engineering. So we could maintain the light weight of those whatever aluminum or metal alloy is, and then without adding additional heavyweight element into this microstructure. Very good question. Thank you. Yes, please.
Does manufacturing the microstructures, and I don't know if this is a stupid question, increase like the permeability of the metal, like for intrusion or like electrical degradation of like the metal? Does it change like other properties of the metal?
That's a great question. I don't know. Maybe if there is an additional influence due to the presence of nanostructure, then it could be. Otherwise, maybe no.
Wenwu, from your presentation, it was not clear when you say fatigue, are you just doing one cycle that you showed, or is that, or if you're doing many cycles, where is that progression that you showed that cycle? Is that a high cycle, low cycle, 50?
Very good, thank you very much. I forgot to mention that. Particularly in the simulation I have done, it was a low cycle fatigue, and I applied in the simulation only 10 cycles. Right. So and the strain amplitude was 5%. Yeah.
So typically when you do these kinds of things, you do ratcheting, right? So not just a constant amplitude for low cycle. If you do, you can see the plastic strain accumulation.
Right.
Why do constant amplitude?
The sinusoidal profile.
But you do ratcheting where you increase the amplitude, even when you do the test, right? You don't do for low cycle, you just don't do constant amplitude, you do the ratcheting.
Right. Yeah, and that could be the reason we chose that sinusoidal profile is it seems like it is also can be done in experiments. And you are absolutely right. We should also examine other types of profile. That's a very good point. Thank you.
I know, we're going to thank our speaker one more time and thank him for a video you